The entire human body relies on exactly 1 to 1.5 milligrams of a single trace element to prevent our neurology from dissolving. Yet, introducing even microscopic amounts of that exact same element in a raw, jagged metallic state rapidly induces systemic heart failure. Consider two entirely different patients. Patient A presents with symmetrical tingling in their hands, loss of physical coordination, and an actively degenerating spinal cord. Yet their routine laboratory tests show a perfectly normal vitamin B12 level. Meanwhile, patient B arrives at the clinic with progressive deafness, failing heart muscle, and blood that has thickened into a dangerous sludge, all driven by microscopic wear debris shedding off an artificial joint. How does one ultra-trace element cause two wildly disparate physiological crises? And why do our standard laboratory tools routinely fail to detect both of them? To accurately diagnose these derangements, we have to strip the metal completely out of its highly guarded organometallic cage and evaluate it down to its bare ionic state. Billions of years ago, long before atmospheric oxygen existed, primitive anaerobic microbes harnessed the specific reducing potential of the cobalt-carbon bond. They used this high-energy connection to drive early DNA synthesis in environments rich in sulfur. Over evolutionary time, humans completely lost the enzymatic machinery to build that highly complex organometallic cage. We cannot synthesize it, nor can we attach raw cobalt into it. We are locked into a strict, non-negotiable reliance on a symbiotic food chain. This creates two massive biological ironies. First, plants contain absolutely no native cobalamin pathways. Second, the trillions of microbes inside the human colon manufacture massive amounts of it, but this occurs anatomically below our only specialized absorption receptors. You produce a vital supply that is simply lost in your waste. To understand how we manage this limitation, we will deconstruct 5 architectural pillars: cobalt's chemical identity, its total body distribution, its homeostatic regulation, its toxicological threat, and the precise laboratory analytics required to measure it. Because we cannot manufacture it and must acquire every single molecule through our diet, the human balance of cobalt is uniquely precarious. This schematic displays the Corin ring. It functions like a microscopic catcher's mitt made of carbon and nitrogen, holding a single highly reactive cobalt ion safely in a flat, planar conformation. In the cell cytoplasm, this cobalt core operates a specific enzyme called methionine synthase. It pulls a methyl group off a circulating folate molecule and transfers it to homocysteine. If the cobalt core is missing, the folate becomes permanently locked at the delivery dock, a condition known as the folate trap. Without that methyl transfer, bone marrow DNA synthesis halts entirely. Inside the mitochondria, cobalt operates a different pathway. Bound as adenosylcobalamin, it drives the MUT enzyme to clear a highly toxic metabolic byproduct called methylmalonyl-CoA. If this mitochondrial pathway fails, the methylmalonyl-CoA backs up. The human body reacts by synthesizing abnormal branched-chain fatty acids. It then mistakenly incorporates these dissolving, faulty fatty acids directly into the nervous system, aggressively stripping away the protective myelin sheath of the spinal cord. The free metal possesses zero biological utility on its own. Its physiological value is strictly dictated by its successful integration into these two precise enzymatic loops. To get that caged cobalt out of our food and into ourselves requires a highly precarious 4-stage digestion relay. In the stomach cavity, hydrochloric acid frees the B12 from dietary protein. Instantly, salivary glands secrete a protective blanket called haptocorin to prevent the acid from destroying the molecule. Simultaneously, specialized gastric cells secrete a separate transport protein known as intrinsic factor. As the relay moves into the alkaline duodenum, pancreatic enzymes strip away the haptocorin blanket. The freshly exposed B12 immediately binds to the intrinsic factor. This creates an armored complex that survives the long transit to the terminal ileum, where specific QBAM receptors finally pull it into the bloodstream. Once absorbed, the human liver hoards about 60. A person can consume a perfectly balanced diet, but the cobalt passes through their system entirely unabsorbed, silently draining the liver's reserve over years. The hypercomplexity of this multi-organ absorption cascade ensures that functional cobalt homeostasis remains incredibly fragile. When raw, inorganic cobalt ions shed from arthroplasty wear debris and enter the bloodstream, they lack that organic corrin cage entirely. With no coenzyme utility, they invade the surrounding tissues as destructive xenobiotics. Free cobalt behaves as a molecular imposter. It slips into the specific enzymes that monitor cellular oxygen levels and physically displaces the iron at their core. This permanently deactivates the cell's hypoxia off switch, a protein called HIF-1 alpha. Even though the patient is breathing normal room air, the cells falsely report severe suffocation. The surviving HIF-1 alpha protein travels to the nucleus and triggers massive erythropoietin production. The bone marrow floods the vascular space with red blood cells, resulting in a dangerous secondary polycythemia. At the exact same time, the raw metal infiltrates the mitochondria. It competes with calcium to block the aerobic pyruvate pathways. The cardiac muscle fibers essentially suffocate from the inside out, leading to fatal dilated cobalt myocardiopathy. Stripping the element of its macrocyclic cage transforms it from an essential genomic protector into a systemic cellular suffocator. Detecting cellular starvation requires accurate laboratory data, but standard automated B12 testing has a severe pre-analytical vulnerability when dealing with autoimmune pernicious anemia. Inside a core laboratory, the B12 assay uses harsh sodium hydroxide to tear apart binding proteins and measure the cobalt complex. However, robust anti-intrinsic factor autoantibodies from the patient's own blood routinely survive this denaturing phase. These intact autoantibodies physically jam the assay's solid phase matrix. The lab analyzer misinterprets the jammed sensor as a massive signal, tricking the machine into reporting a perfectly normal, falsely elevated B12 result. To expose this illusion, clinical pathologists must bypass the B12 number and measure the chemical exhaust. They order tests for methylmalonic acid and homocysteine. If those two backup metabolites are severely elevated, it proves the intracellular cobalt machinery has stalled. Relying strictly on automated B12 numbers without interrogating the metabolic context can lead a physician to discharge a patient whose spinal cord is actively dissolving. Conversely, finding raw toxic cobalt ions requires intense mass spectrometry physics. Laboratories incinerate the patient's blood sample inside an argon plasma torch, burning at 8,000 Kelvin, ripping every compound down to its bare atoms. This readout scale illustrates a major physical limitation. Inside that chaotic plasma torch, matrix elements frequently fuse together. An argon atom bonds with a fluoride atom, or calcium bonds with oxygen. Both of these accidental molecules carry an atomic mass of exactly 59, perfectly mimicking the native cobalt atom the machine is searching for. To resolve this isobaric shielding effect, scientists employ kinetic energy discrimination. The ion stream is forced through a collision cell flooded with helium gas. Because the fake polyatomic molecules are physically bulkier, they constantly crash into the helium atoms, losing momentum and dropping out of the flight path. Only the dense, true cobalt atoms slip cleanly to the detector. Yet even this precise physics engine can be compromised before the blood reaches the lab. Standard stainless steel phlebotomy needles and colored rubber tube stoppers will leach microscopic manufacturing cobalt directly into the sample, requiring strict use of royal blue trace element tubes to avoid pseudo-hypercobaltemia. Accurately quantifying ultra-trace metal toxicity requires laboratories to defeat both omnipresent environmental contamination and the fundamental physical limits of elemental mass. For patients with metal-on-metal hip replacements, international consensus guidelines establish a strict safety limit. A whole blood cobalt concentration exceeding 7.0 micrograms per liter is the definitive panic threshold, indicating a severe risk for localized tissue necrosis and systemic poisoning. Crucially, metallic wear debris circulates as particulate fragments that partition differently between erythrocytes and plasma. Therefore, whole blood is the only clinically acceptable matrix for tracking these implants over time. Serum testing will yield inaccurate trends. Pathologists must also track chromium levels and renal filtration rates alongside the cobalt. Because these metals are cleared by the kidneys, a drop in filtration can cause serum metal concentrations to spike rapidly, even if the physical implant is perfectly stable. Managing systemic toxicological derangements requires rigid adherence to these analytical algorithms to prevent surgical misinterpretations of volatile trace data. A normal automated B12 result When paired with macrocytic anemia and elevated methylmalonic acid and homocysteine, definitively confirms autoantibody-masked pernicious anemia. Furthermore, the sudden onset of unexplained polycythemia in a patient with a metal joint replacement is a massive clinical red flag for HIF-1 alpha stabilization driven by raw cobaltism. Biologically, cobalt is strictly an organometallic engine. It requires a highly complex, vulnerable, 4-stage absorption relay simply to enter the human system safely. When clinical presentation contradicts the lab report, pathologists must anticipate the autoantibody mask, recognize the destruction caused by inorganic toxicity, and utilize kinetic energy discrimination physics to uncover the actual tissue-level truth. Clinical pathology serves as the vital diagnostic bridge, connecting macroscopic patient symptoms directly to atomic reality. Cobalt perfectly illustrates the razor-thin margins of biological engineering. We require the exact, unyielding structure of the Corrin ring to safely harness its power. Strip away that structure, and the architect becomes the destroyer. Next time, we step away from the trace elements that drive our DNA and examine the heavy metals that threaten its very structure by deconstructing lead, because human architecture is defined by these exact, unyielding chemical boundaries.